Hello, everyone. Welcome to New RIPS 2021. And this is Huck from Georgia Institute of Technology. So today I'm gonna present our work at offline reinforced learning workshop. So our presentation topic is pessimistic model selection for offline deep reinforced learning. And this is a joint work with my collaborator, Professor Chen-Ling Qi from George Washington University, who is also the equal contribution as the first author, co-first author, and Professor Yifan Cui from University of Singapore, and Dr. Pingyi Chen from IBM Research AI. So yeah, this is the team, and I'm the presenter, and Professor Qi, Professor Cui, and Dr. Chen. We have a full version about this work. We put it in archive. So if you are interested, you can check the link here. So first, I want to talk about the motivation about this work. So our motivation is when we do the model selection for deep reinforced learning, especially in the offline setting. So sometimes we have the overestimation issues. So we coming from an idea saying our model selection process could be more pessimistic. So we call this idea pessimistic model selection. We call it PMS. So what PMS actually do is saying we have a detective is trying to do the model selection. So first, saying we have a different type of offline reinforced learning models, saying the model 0, model 1, and model 2, and model 3 here. So we know, like, because we couldn't offline, tuning this parameter and rerun it again in the online simulator. So how can we estimate which model could be the best model to perform its online learning and reward attentive approaches is an open problem. But the idea presenting this work is providing a way to estimate and select one of the best model. We know we can estimate it from our best model for offline reinforced learning. So here's the outline about this work. First, we'll introduce some theoretical foundation about this work, and then we'll introduce our pessimistic model selection algorithm, and then there will be some experiments on the deep reinforced learning environment, and finally we'll build the conclusion. So first, we want to have some background about this work. So we all know in the reinforced learning, we have the optimal Bellman equation to help us to maximize the Q value by the expectation. And then we also have a function called the discount probability ratio function, which is trying to have a discount probability ratio. So the estimation about the ratio function is motivated by the observation that every measurement function that holds this equation 3 we have. And then another thing we have to use is the double robust estimator, which is motivated by the estimation inference function of the value function under a transaction sampling setting. So one of the good references from the paper of Kelas and Uehara in 2019. So one of the nice property of the double robust estimator is that as long as the Q function or the ratio function can be consistently estimated, the final estimated it could be also consistent. So here is the ratio function we have, and here's the Q function we have, and then finally we can have a consistent final estimator. But why we need this pessimistic model selection algorithm for alpha reinforced learning? Here we want to review some difficulty and challenge. So first, there can be easy overestimated Q function due to the max operator, especially when some state action pairs are not sufficiently visible in the batch data. So we all know because in the realistic setting, when we try to collect as more as we can in the offline batch data, but they are still not really sufficient. In the most insufficient settings, the estimation of the Q function can be overestimating, and finally, you can also overestimating some ability for a certain model. And second challenge could be no ground truth for the value function of any policies. The offline policy evaluation, which is the OPE procedure on this validation dataset, cannot avoid involving to additional tuning on the hyperparameter. That means in this case, we want to have a partially and parameter-free tuning algorithm in the offline model selection setting. We don't want to tune this model parameter. We only want to do the selection. Finally, we have an issue from the cost validation because for the data set undergoing this cost validation process, because we still have these dynamic issues. And if we do the cost validation for this offline data, so we often ignore the Markovanian dependency, which will cause additional errors. So our approach is trying to addressing this potential challenge by proposing a new selection algorithm based on some theoretical finding, which is the theoretical part is the main contributions of this work. So before we go into the detail, let's have some notation of a batch dataset. So especially denote the index of our batch data, which is the DN here. So we can have the J functions, the J numbers, and we divided this J into all numbers of non-overlapping subsets, saying the J1 to JO, and the corresponding data subset can be denoted D1 to DO, which is the batch data we care about. And finally, without loss of generality, we assume this data subset have equal size. And then we require this aggregation trunk for the data for our offline model selection. And then another notation we care about is the L. So for example, we have a total numbers of capital L, and then we care about each L model which can perform the best. And then after having this notation, we will have the background for sequential model selection. So to improve the efficiency and the robustness of our value function estimation for each candidate model, we have to compute the estimated value function of the policy on each data set, which is the offline batch data. So here we have the estimation of our value function here. So which is the most important part is this empirical average over the data set. So when we aggregate the estimation value functions, we actually want to deal with this uncertainty of this estimate due to the finite sample estimation. And then we divided an uncertainty quantification of our estimated value function for each candidate model. So which is here. And estimation procedure stop once we use all of our offline data. And then here is the proposed pessimistic model selection. So which we have the weighted average over all the intermediate value functions, which is here. And then we have the variance here. So how can we interpret these pessimistic model selections? So, for example, given a confidence level of alpha for each candidate, which is L here, we can compute the U functions where we have the standard normal distribution, and then we can have our selection from this old L function by maximizing the U function. But why this U function is important? Because the proposed pessimistic idea is to addressing the overestimation issues of the value or the Q function in the offline RL setting. And the definition of the Q function is coming from the pessimistic like hypothesis. So here is our algorithm overview. So saying we have our data set, and out of candidate models for estimating optimal Q function and the policy, and we divided this the offline data set into a non-overlapping subset, as we say, the D1 to D0, and then we require that for any one and over this this trunk, and then we can have our J over time and each individual here. So for each model, we construct the optimal Q and the policy using the data subset, and then we compute the ratio function using this each offline batch data. So we get inspiration from this Nordstrom's paper and the minimized solvers for this equation 3. And then we compute our estimation of our value function and the variance using this D offline batch data again. And finally, we compute our U functions, which is coming from a pessimistic hypothesis and perspective. And finally, we can have our best candidate model from selection, which is the line 9 here. And then as the select model, and we run the algorithm on the full data set again to obtain the final policy. So by having this selection, we actually have some technical assumption. So the assumption 1 is the stochastic process is stationary with stationary distribution. And then our assumption 2 is for every candidate model and the data trunk, we have a expectation for some constant C and some constraint here. So for assumption 1 is actually standard in the existing literature, such as the Colus and the Hana in 2019. And for the assumption 2 is key to our developed results, and state all the candidate model are good enough, so eventually their value function will converge to that of the optimal value function. So here is our theoretical result in our theory 1, which provide a uncertainty qualification of each candidate model using policy optimization. So here is our theory 1. And in our corollary 1, so we consider the worst performance of each candidate model and guarantee that the select model is the best one with higher probability. So we want to say maybe in the Oracle, we couldn't model, sometimes we didn't visit that Oracle model, but we can select the best model from our selection models as far we have eventually. And then a lower confidence limit of the value function, which is something we care about here. So since we have some assumption during this model selection process, so we also relax assumption 2 by allowing possibility both non-negatable bias in estimating the optimal policy and introduce 2 refinement approach for addressing these issues. So, and then we have our assumption 3 and assumption 6 here. The details you can find in our paper. And finally, for the refinement approach of this pessimistic model selection algorithm, we have our theory 2. So theory 2 is actually motivated by the Lipsky principle from a non-parametric statistic and studying the model selection of the offline policy evaluation. So we finally ranked the L candidate model in a non-increasing orders based on this variance. And we actually select different deep reinforcement algorithm for our experiment. The first is tubular data as a frozen lake. And then we have our navigation task from the banana collector. It's trying to collect a yellow banana to attain a world and then trying to avoid the purple banana. So the agent will have this sensor data, and then they can control the direction about how the car is moving. And we collect this data from a offline simulator with this offline from an online simulator, and then collect this offline batch data. And then the popular Atari game Pong and Breakout, and the half cheetah, and finally we have the worker from the Mojoko simulator. So our first experiment results interesting because we can find out in some others exceeding approach for the model selection, people ignore some models, although they can have really good true policy value, which is here, but the OPU value may not be as good as their true policy value. But in our PMS, you can see we can actually pessimistically select those models, and then those models are among the top of the model, which can have a better true policy, the value on the true policy. And then if we look at our top K ranking based on the regrades and the positions, you can find out we select different alpha setting, for example, DQN and DQN in a PMS setting, batch behavior coloning, and PMS with behavior coloning. So the dashed line is without PMS, and the bold line is with PMS. You can find out with PMS, the regrade become much smaller, and the precision become much higher with the PMS. And finally, we want to highlight based on the refinement results, the PMS don't have a depends on the hypothesis, but in our deploy DR development, the PMS in different refinement don't have a large difference. And here is our conclusion. So we propose a new series-driven model selection framework for offline deep reinforcement learning based on statistical inference. And the proposed PMS can warrant that the worst performance of the select model is the best among all the candidate models. And finally, PMS algorithms show competitive results in different offline deep RL developments such as navigation, Atari game, and continuous control. And thank you for listening. We will see you in the poster section, and that's it. Thanks.